What if a liquid could freeze and still flow at the same time? That's not science fiction anymore. Physicists have just observed something that challenges one of the strangest ideas in quantum physics, a superfluid that turns solid. Let's break down what they found and why it matters. Normally, matter follows a simple path as it cools down. Gas becomes liquid, liquid becomes solid. End of story. But the quantum world never plays by simple rules. About a century ago, scientists discovered that helium, when cooled to extremely low temperatures, becomes a superfluid. In that state, it flows with zero friction. It can climb walls, leak through microscopic cracks, and move forever without losing energy. It's one of the most bizarre phases of matter we know. That discovery raised a deep question. If you cool a superfluid even more, does anything happen next? Or is frictionless motion the final stage? Physicists have been chasing that answer for nearly 50 years. Now, a new experiment reported in Nature suggests we finally have a clue. A team led by Corey Dean at Columbia University and Jolly at the University of Texas at Austin observed a superfluid that did something unexpected. It stopped flowing. At very low temperatures, instead of becoming more superfluid, the system froze into a solid-like state while still showing signs of quantum behavior. In simple terms, they may have observed a supersolid. A supersolid sounds like a contradiction. A normal solid has atoms locked into a rigid, repeating pattern. A superfluid, by definition, flows freely without resistance. A supersolid is predicted to combine both crystal-like structure and frictionless quantum motion. For decades, helium was the main candidate. But despite enormous effort, no one has conclusively shown helium naturally turning into a supersolid. Other experiments created supersolid-like states using lasers to force particles into patterns, but that felt artificial. What physicists really wanted was a self-organized supersolid, emerging on its own. That's where graphene comes in. Graphene is a single layer of carbon atoms arranged in a perfect crystal. When researchers stack two graphene layers and carefully control their electrical properties, something interesting happens. One layer is filled with extra electrons. The other has holes, places where electrons are missing. Electrons and holes attract each other and bind into pairs called excitons. Under a strong magnetic field, these excitons can behave collectively and even form a superfluid. The team then started tuning the system, adjusting temperature and exciton density. That's when things got weird. At high density, the excitons flowed like a normal superfluid. But as the density decreased and the system cooled further, the flow suddenly vanished. The material became an insulator. No movement, no current. Even stranger, when the researchers raised the temperature again, the superfluid came back. This is the reverse of what physics usually expects. As Jolly put it, superfluidity is normally the lowest energy state. Seeing an insulating phase that melts into a superfluid strongly suggests the low-temperature state is an exotic quantum solid, possibly a supersolid. Is it confirmed? Not yet, at least not beyond doubt. Measuring a solid that doesn't conduct electricity is extremely challenging. The team currently relies on transport measurements, which stop working when nothing flows. But all the surrounding evidence points to a new quantum phase, one that doesn't fit neatly into existing categories. And this is just the beginning. Why does this matter? Because excitons are much lighter than atoms like helium. That means quantum states like superfluids or supersolids could exist at much higher temperatures in 2D materials. If researchers can stabilize these phases without strong magnetic fields, they could unlock entirely new ways to control quantum matter. For decades, supersolids were a theoretical curiosity. Now, thanks to graphene, they're starting to look real. And once again, the quantum world reminds us. Even when things freeze, they don't always stop moving.